All right, this is going to be the second video on chapter 14. And we're going to be discussing integrated rate laws. So last time we were just looking at the rate law expression where we had rate equals K and then the concentrations. So that's your ordinary rate law. The integrated rate law is one that relates time and concentration, and we didn't have time involved in our rate law. Okay, so if we consider this reaction, the rate law, like we wrote in the part one, was rate equals K times the concentration, and that would be of the reactant. And then the average rate would be the change in concentration divided by time. So if we set those equal to each other, since they're both rate, we would get K times the concentration of A equals change in concentration divided by time. If we rearrange that expression, we would get the change in concentration over concentration is minus K change in time. And then if we do the natural log of that, we end up with this equation. Finally, rearranging it, we would get ln of A equals minus KT plus ln of A0, and A0 is that initial concentration. Now, what is important about this is that this matches the format for a straight line, y equals mx plus b, meaning if I plot ln of A on my y-axis, minus k is my slope, t is my time, which is plotted on the x-axis, and then my y-intercept would be ln of the initial concentration. So if I make a plot of ln of A on the y-axis and t on the x-axis, I would get a linear equation, and I could use graphical analysis to plot that, and then I could find the slope of the line, and the slope of that line would give me K, which is my constant. All right, so in this case, they have plotted, in this case, pressure versus time, or ln of pressure. So instead of using pressure, we're using concentrations because this is a gas. But you can see if I just do pressure versus time, I get an exponential curve. But if I do ln of the pressure versus time, I get a straight line. And the reason this one is going down is because we said that the slope was minus k. So the minuses would cancel, and whatever the slope of this line was, that positive value would tell me my rate constant. Okay, so this slide sums all that up. It says if we plot ln of the concentration versus time, I'm going to get a straight line, and the slope would be minus k. All right, so here is an example where we're going to use that integrated rate law. It says the decomposition of a certain insecticide at 12 degrees Celsius follows first order kinetics, and we would have to know what the order was because we're going to have three different integrated rate laws, one for zero order, one for first order, one for second order. It gives me the rate constant, and it gives me a concentration, and they said assume that the temperature is constant. They want me to find the concentration later and how long it's going to take, the time. All right, so my rate law is ln of A equals minus KT plus ln of the initial concentration. What I was given was the initial concentration, I was given the constant, and I was given the time, which was 1 year. So I'm going to plug in my K, and I took that times 1, so I got that. And this was my initial concentration. I added those together to get this. Now to get A, I have to do the inverse of the natural log, which is e to that exponent. So I need to do e to the negative number. I get this value, so that means this is my concentration after a year. Now the second part of this question asks me to find time. So I'm going to use that same equation. So this time I'm going to plug in the concentration that they gave me later, the initial concentration, and my K value, and I'm going to solve for time. and I got a time of 0.35 years. Now, if it's a second order reaction, then K equals A squared, the 2 here representing my order. Rate is also equal to change in concentration divided by time. So just like last time, we're going to set those two equal to each other. And then we're going to write it in the format that looks like a straight line. So in this case, I would plot 1 over the concentration. That would be equal to KT, which is K again is my slope. T would be on the x-axis, and my y-intercept would be 1 over my initial concentration. Okay, so if this is second order, notice if it was first order, I do ln of concentration versus time. That's not a straight line. But if I do 1 over concentration versus time, then I get a straight line. So that's telling me that this is second order because I get a straight line when I plot 1 over the concentration versus time. Okay, so it gives me the following data were obtained, and they want to know if the reaction is first or second order. So what you need to do is you would open up graphical analysis. You would put concentration in your y-axis. You would put time in the x-axis. And then you would make plots. You would do natural log of the concentration, where you would put, this would be a calculated column where you would put natural log of the concentration that you entered. Here would be another calculated column, which would be 1 over the concentration. And if you plot natural log of concentration versus time, we don't get a straight line. If we do 1 over concentration versus time, we get a straight line telling me that it's second order. If the first one happened to be a straight line, then that means it would have been first order. All right, zero order reactions means that when we change the concentration, it doesn't have any effect on the rate. So rate is equal to K. There are some zero order reactions. And in this case, if I plot concentration versus time, I would get a straight line. And the slope of that line would be minus K. So that means that there would be 3 graphs that we would want to plot. We would want to plot concentration versus time. If that was a straight line, it would be zero order. If we plotted ln of my concentration versus time, that would be first order. And if I plotted 1 over concentration versus time, then that would tell me it would be second order. All right, now we're going to talk about half-life. And the half-life is the time that it takes for half of the initial concentration to be used up. So if it's a first order reaction, this is my integrated rate law. And I know that the concentration later for 1 half-life would be half of the initial. So 1/2 of A0. And then for T, I put in T sub half, which represents half-life. That doesn't mean you're going to be dividing that by 2 or anything. That's just how we denote half-life, T sub half. Okay, so now we're going to go ahead and clean up this equation. And when we do that, we find that the equation to find the half-life for something that is first order is 0.693 divided by K, where K is your rate constant. Now, if we look at something that is going to be second order, then we would use the second order integrated rate law. And again, the concentration later would be half, after 1 half-life would be half of the initial concentration. And then I would simplify this equation so that the half-life would be 1 over the rate constant times the initial concentration. So I have a different equation if it's a second order half-life.